Hello, good evening. Welcome to the first TA class of Electronic Theory of Solids. I don't know whether I'm audible or not. Please confirm the same. Yeah, good. Now let's start the class. Welcome to the course Electronic Properties of Solid. It's a theory of solids. As you know, this course is being offered by NPTEL in the tenure of January to April 2026. And I'm the TA for this course. Myself, Mohit. I'm a PMRF research scholar at ISC Bengaluru. Currently in the fifth year of PhD. I primarily work on electronics properties of this graphene, exploring them along with the artificial superlattices. I'm currently working in graphene-based system, graphene HBN superlattice-based system. Primarily changing the periodicity in the uh, graphene, and then seeing the consequences like break gap opening, all those things which we'll be seeing in this coursework. Those are the things which we realize experimentally. Yeah. And as you know, the instructor of this course is Professor Aragya from IIT Kharagpur. And this course aims for the students who are there in the UG or in the PG level. So I'll just give a brief overview of this course, like what I will be covering in this course through the assignment and the solutions, and then we'll start the our problem solving session, which will be aiming for the assignment 0. So if I say overview of this course, so in this course, we'll be studying how electrons behave in solids and how their behavior determines the electrical, magnetic and the quantum properties of the material. So if an electron is there, how it flows into the material. So in the material, and their correlated phases which are giving these electrical, magnetic, and then the quantum properties of the matter. Yeah. So we'll begin very simply with the model starting from like two atom solid, and then we'll be gradually building upon them, right? Like the tight binding model, all those things. So they are essential to explain why we'll be addressing why few materials are metal, few of them are insulator, and some of them are semiconductor. So we'll be addressing why some materials are metal, insulator, or semiconductor, and then addressing them, we'll be covering like the free and independent electron model, like the true day, which will be covering the free electron model, and then we'll be covering the Fermi-Dirac statistics, transport phenomena like conductivity and the Hall effect. This Hall effect is very important in the sense that at the high temperature and the low magnetic field, there will be classical Hall effect. If your system high D and at high temperature and high T and low B, but if you make your temperature small enough compared to the gap between the Landau levels, you go on to the quantum Hall effect regime, where classical mechanics falls down, and this is something which we'll discuss when we'll be discussing the Hall effect. And on these things only we'll be building up, and then at the last we'll be addressing like the spintronics and the related emerging phenomenon in the case of the graphene, nanotubes, and superconductivity. So this is something which we'll be covering in this course, and the physics behind these phenomenon and why it emerges. So this is the basic overview for this electronic properties of the solids. Now, having said that, I will start the class with uh, opening up with it like uh, assignment questions. And the first question which I'll be asking is, what is effective mass and how can we determine the effective mass from the dispersion? So this is something with which I'll start, and I'll show you how to derive the effective mass from the dispersion. So let's say the question number one. Yeah. Let's say the particle, for a particle of dispersion, E is equals to h bar square k square by 4m, where m is some mass, like let's say the electronic mass. Then determine the effective mass. The effective mass. So what is this mass m here? And effective mass, let's say m star. So the question first which we should ask is, what is the difference between what is actually effective mass? What do we mean by effective mass? See, when if let's say an electron is moving free, its mass will be electronic mass, right? Its mass is me. That is roughly around 9.1 into 10 power minus 31 kg. If I'm not wrong, I think that's what the electronic mass is. But if the same electron is now confined to some lattice, electron in lattice, let's say there is a lattice like this, and these atoms also have their potential. Now, if this electron moves through this lattice, right, it will encounter some attractive force towards these positive ions which are there in the system, and because of that its dispersion will be modified. Now instead of here the 4 electron, we know E is p square by 2m, and p is what, h bar square k square by 2m. But if your dispersion is slightly different, then in that case you might get a dispersion which is h bar square k square by 4m. Let's say that's what we have in our question. So in that case, now your electronic mass, you can write like 2 and then 2m. So your effective mass basically, which the electron will now feel in the system in the presence of the external forces. You can still model your system as the free particle, but you know that your electron is not free. Now it's confined in the lattice. And in that case, if you want to understand the physics of that electron in form of the free electron model, then you will have to assign a mass which should be equals to 2m. And this is what is known as effective mass. So this m star will be 2m for this case. But there is an there is another way which here the dispersion was very simple, so you can just model it like this. But if the dispersion is slightly complex, in that case your m star will be given by h bar square and the second derivative of energy with respect to the wave vector inverse. So if we plug in our case that our energy is h bar square k square by 4m. So let's take the single derivative, so del E by del K, that will be 2 h bar square K by 4m, that boils down to h bar square K by 2m. And now you take the double derivative, so del 2 E by del K square, that gives you h bar square by 2m. So this is your equation 1, this is your equation 2. Now if you plug equation 2 into equation 1, then what you get is the effective mass for that carrier, and that will be h bar square times 2m by h bar square. That is equals to 2m. This is what we evaluated if we write our dispersion in the form of h bar square k square by 2m star. So here also we got the m star to be 2m, and this is another way of a more accurate way of, like, if a dispersion is slightly of the complex form, instead of k square it is of the k4 k cube, then this is how you calculate the dispersion, the effective mass basically from the dispersion. So if you have any question to ask, you can ask in the class also, so I'll be happy to address your concern. So this is the first question, which is about the effective mass of the carriers. Okay. Now moving forward, we can. I'll take the next question. If there is no question from your end, that let's say you have an electron. This is about the boundary condition. Boundary condition. Yeah. So you have an electron of mass m, which is confined in a which is confined in a 1D box. In the infinite box basically. Infinite potential. Well, you can say, or box you can say. And now I ask you, like, okay, the potential well of, let me define the width also, or width A, right? And then
என்னாச்சு இது? நம்ம குடும்பத்துல ரொம்ப வருஷத்துக்கு அப்புறம் வரப்போற புது உசுரு இது.
what will be the energy levels for it, right? So this is the question, and the energy levels, I'm asking the ground first and the second excited energy level. Okay, so if I have to write down the equation, write down the problem in detail, then it think it like this is a box which you have whose width is a. It's a 1D box, so electron can only move in one direction. Let's say this is x direction. So electron can either move in x or minus x. And y and z are constrained according to the problem. And now you have an electron which is there in the system. Now the quantum mechanics says that okay, electron, and in this case the energy levels are quantized. Continuum states are not allowed. So we'll have to first see what the wave function for this electron will be. So the electron, if it is confined in the 1D box, it's a basic quantum mechanics problem. We all know that it's psi x will be under root 2 by a sine n pi x by a, right? If you compare this with this one, sine kx, right? Then what you get, your wave vector as n pi by a. Since outside this box, your potential is infinite, inside the potential is zero, is the 1D box. In that case, inside the hole, the energy of your carrier will be h bar square k square by 2m, right? If you replace, if you substitute equation 1 in 2, then what you get is your energy, which is h bar square n square pi square by 2ma square, where n can belong to integer and n has to be greater than equals to 1, and n can't be 0 because 0 energy is not allowed from the quantum mechanics, because delta E delta T has to be greater than h bar by 2, Heisenberg uncertainty principle. Right? If that's the case, in that scenario, your ground state energy will be n equals to 0. So E ground will be n is equals to 0, and n is equals to 1, and that will be pi square h bar square by 2ma square. Now, if I ask you the first excited energy, E first excited, that will be n equals to 2. That will be 2 square pi square h bar square by 2ma square. This gives you 2 pi square h bar square by ma square. Similarly, you can ask the second excited also. For the second excited state, your n will be 3, and that will give you 3 square pi square h bar square by 2ma square. That gives you 9 pi square h bar square by 2ma square. This is how you calculate the first, second, third, and subsequently the higher energy levels. If you want to ask for the wave function, then you can also draw the wave function. For k is equals n is equals to 1, you know the wave function will be of this form. For n is equals to 2, the wave function psi x will be of this form. For n is equals to 3, the wave function will be of this form in the 1D well. And this is how your wave functions will look like, psi k. So these kind of problems are like the boundary condition problem, and they will appear when we will go on solving the electron in a periodic lattice, because then you can model your electron like, because in crystal what is there, they are like separated by distance a, right? All of them are identical kind of thing. So then you apply the boundary condition that whatever the wave function is here at this point, the physical measurable quantity should here and here be same on one and the, let's say, third atom, right? And then you use the boundary condition, the quantum mechanics, to get the electronic dispersion out of it. That's how we solve nowadays the problem in the Bloch theorem. So this is the fundamental of the Bloch theorem, these boundary conditions, and fundamental of the today's quantum mechanics and the tight binding model. So this was about the second problem. Now, if you have any question, you can ask. Okay, if there is no question, then I will go on moving to the next problem. So the next problem which I will take will be, you have you have a conductor, let's say you have a metal is there. In this metal, in this piece of metal, you apply a voltage here, V1, you ground this one, and you measure the current in this metal. This electrical conduction happens, right? That's why you get the current. If your I is 0, then it means there is no electrical conduction. The more the I, the better the electrical conductor. So the electrical conduction is primarily because of what? Let me give you four options. The first one is ions. The second one is holes. The third one is free electron near the Fermi level. And the last option is bound core electron. Do anybody have answer to it? This is the basic of this condensed matter physics, right? This is what we keep saying, like in our day-to-day life, that okay, the electrons which are there near the Fermi level, they only contribute. But can anybody explain it, like why it is so? Okay, let me then. Okay, the correct answer to it is like the free electrons which are there near the Fermi level. And how it is come? It comes is like, let's say at this point you are applying a bias, right? That this is the energy scale which I'm drawing. Energy, and this is your chemical potential of V1. So the chemical potential will be EV1 on this side, and on this end you have grounded your sample. So this difference is EV1. This is your ground, which is, let me call this reference 0, right? And in between you have your metal. So I'm drawing the electronic states. So till this point, this is the Fermi energy which is connected, and then these are the free electrons. So think it like a liquid flowing from EV1 to 0 in this direction, right? So you can model it like this. So the electrons which are there in the bottom, they are the valence band electron kind of thing. They are bound and they will not flow because there is no difference between the chemical potential here and here for these electrons. They are at the same potential, so they will not flow. The carriers which will flow will be near the Fermi energy, which are of this much region, EV1 of the Fermi energy. And this is why the conduction happens in the electron in the metals, and that's the reason why these insulator don't conduct, because here in that case, for this is for the metal, they have available states there. But if I draw it for insulator, the picture will be, this is EV1, similarly 0, this is your ground, your potential, and in your insulator your band is, you have a band gap here, so your electronic states are till at this point only, and the next available states are maybe from here, they are above. So in this region particularly, there is no available states of this EV1 region, and that's why there are no available state. There's nothing which can carry the current from this probe to the probe on the right, left to right. There is no current, no current. This is insulator band gap. So then there is no current, and so therefore it, these insulators are bad conductor of electricity. So the carriers which are there near the Fermi level, they only contribute to the electrical conduction. Any question?
Do we require to write these notes, or it will be available after like the
They will be available. These notes will be available.
session?
I'll be sharing this after the class, so they will be
Okay, okay.
uploaded on the like. You guys will be provided. I think you would have been provided a link where all those notes and the recordings will be there. Class recordings will be there.
Okay, okay, okay. Got
Okay. So now, if this is clear, then I will take on some quantum mechanics part question, which will be based on the group velocity. So let's say if you are given, if a tight binding dispersion is given. Tight binding is nothing but just it's a model formation in which you model the electrons which are like initially well separated, then you bring them closer, and electrons were initially bound to that atom particularly, but now if you bring the atoms closer, the electrons gets more delocalized, and then you solve those models to get the electronic dispersion. So it's just the name to that, the way of doing the problem. So in a tight binding dispersion, you get your ek, which is your energy, k is your wave vector, as e naught, which is a constant, minus 2t. No, so t is a hopping parameter, cos ka. K is a wave vector. So t is generally constant for like a lattice kind of thing. Like what is the energy requirement from hopping from one atom A to atom B? So you can think it like if you have a lattice here. So one, two, three, these atoms are there. So what is the probability of atoms hopping from 1 to 2? That what is the energy required for the electron to hop from 1 to 2? That this is the T. If the atoms are far apart, you know the T will be large. If the atoms are more closer, then the T will be small. Yeah. So in this kind of the dispersion, what is the group velocity? Group velocity is something like with which your wave packet will be traveling in your this electronic dispersion. How the total flow of electron will be determined. So what will be the group velocity of an electron? Yeah. So We all know that the group velocity E, V is 1 by h bar del E by del K. So if this is the dispersion which you have, in that case, let's take the first derivative of the energy. That will be, if you take the derivative of del E naught by del K, this will be 0 because E naught is a constant, minus 2t. If you take derivative of cos Ka, then it will be sine Ka, right? It will be of the sine form sine Ka, and multiplied by A. Because if you're taking the derivative, the factor which is there in the multiplication of the K will come out. So the one what you get is 2t A sine Ka, and in that case your group velocity V group will be 1 by h bar 2ta sine Ka. Yeah. So this is how you calculate the group velocity. If you are given a dispersion of any form, you can calculate the group velocity using this relation. The interesting part comes, like, I don't know whether you guys know about the graphene or not. So graphene is a 2D material. It's a 2D material which has this very peculiar electronic dispersion, which is linear h bar kbf. That's why it's also known as Dirac material, because it has linear electronic dispersion in the momentum. So if you see, generally what we have your energy relation as h bar square k square by 2m, right? Parabolic spectra we have, and there are no negative energy allowed. But for the case of the graphene, what you have is plus minus h bar kbf basically. So both the positive and negative energies are allowed for the case of the graphene. And along with this, if you take the group velocity is also constant Vf, which is given by the slope of this line basically. And the Vf for graphene is 3 into 10, 1 into 10 power 6 meter per second. Yeah. So why I'm saying the graphene is very different from the normal material is, generally you have the parabolic, here is linear, and there is one more thing where you see the linear. Let me just take you to your maybe graduate level classes, that if you have a photon, right, you can write its energy as E equals to pc, right, where p is the momentum and the c is the speed of light, and p is nothing but h bar k, right? See, if you compare these two, h bar k vf, vf is also has speed of electrons in the system, and here for the uh, photons, c is the speed of light, 3 into 10 power 8 meter per second. So if you see, graphene is a condensed matter system, matter system which help you realize the high energy physics. This is a part of the high energy physics, right? High energy physics, the photons, all those things. High energy physics theories, realize or test the high energy physics theory in the experimental lab, even at very low energies, because here your Vf is 2 order of magnitude less than the speed of light. That's why there are many phenomena that the main idea of the graphene, basically the thin cell theory, which came from the high energy. So sometimes you read a part of the physics, and that it, in the future it links to the and gets applied to the other part of the systems basically. For example, the high energy physics is very different from the uh, electrons in solids. But if you have read about the high energy physics, and then you have some bit of knowledge of the condensed matter system also, you can combine the theories, and you can get something which is like that of the graphene electronic dispersion. It was well predicted ways before, but in 2005, this Andre Geim and Kostya Novoselov discovered the graphene at University of Manchester, University of Manchester, UK. Yeah. So this is the first 2D material, graphene. First 2D material, which was exfoliated. So before that, we did not had the like you say that the 2D material. Before the 2005, we of course had two-dimensional electron gas confined in the gallium arsenide, but not the perfect 2D material. Graphene is just a single sheet of atoms, and they were able to exfoliate it. And this is an interesting story. You might be interested to know these things. They are available on the internet, Wikipedia. You can read about it. That how just using the simple Scotch tape which you have in your home also, they exfoliated this material. No fancy thing. And for this one, they also get the Nobel Prize, I think of the 2005 or 2008. Yeah, 2005, I think. You can check this one. These two guys got the Nobel Prize for discovering the graphene. And now graphene is something which is deriving the major part of the research, not only in India but also in the largest group of the this condensed matter community, being it the MIT, Stanford, Harvard, wherever you go, you will find a group which is working on the graphene. Even in the ISC Bangalore or TFR, people are looking to make the devices out of it. And now the field is towards Plustronics. Those who wants to pursue their career, the PhD or something in the field of the physics, they should give at least some time to the graphene study. That what's the current ongoing researches, and it will definitely motivate you to do the research in the future. Yeah. So this was apart from your coursework. If this is there, then I will take uh, a next question, which is on like if you have a semiconductor and it's intrinsic semiconductor and you want to make it doped, how you can dope it to make it electron like or hole like. So let me put forth the question. Like, so the question is to obtain a p-type semiconductor from silicon. It should be doped with an element having how many valence electrons? Okay, so what should be the answer? Yeah. Okay, so let me just give some options also, so that at least you can say. Let's say that the option is option A is 2, option B is 3, option C is 4, and option D is 5. Yeah. let me just make it because this will also satisfy the criteria. 6, yeah. Okay, so if you don't willing to answer, the thing is like you have
So,
silicon. Hello.
yes, sir, option D will be correct.
Yeah, right,
Maybe.
right. Option B will be correct because you want to make it to be the p type, and if you want to make it the p type, you will have to create a hole, and to create a hole, you will have to basically replace the silicon atom with something which has less number of electron, right? And that's when you get the p type semiconductor, and that's how you dope the semiconductors to make them either the p type, the hole type, or if you want to make them the electron type, the n type. Accordingly, you dope it with the impurity. That's why you call the impurity doping, basically replacing the silicon atoms with something which can make it either n type depending the concentration you put, or the p type. So this is a very well known practice in the condensed matter experimental part, at least, where you make the your wafers on which your chips are there, your mobile chips, whatever your computer through which you are seeing the system, your mobile phone, it has chip built inside, right? And those fabricated chips are of the silicon, and depending on the requirement, they are p doped, n doped, and then they are well polished, and on top of that only your chip lies. So it's of the like the not only the fundamental interest but of the engineering aspect also. You dope the systems to intentionally change the properties. So if you want to make it p type, you dope it. So it has valency for p type. You dope it with material having atom having valency less than 3, less than 4. So if you see the options, option 3 B is the correct one. Yeah. So this is, I think it was question number 5 or 4, I don't know. Yeah, 5. Okay. If time permits, I will take on the one more question. This is like about uh, the arrangement of the your ions or atoms in different crystalline structure. This is something which we read in our 11th class standard, as far as I remember when I was there. So let's say you have an FCC structure, and I ask you how many, what is the coordination number? What is the coordination number in this lattice structure? Yeah. Do anybody have answer to it in the FCC? Like, what is the coordination number? Okay, let me give some options also. A is 4, B is 8, C is 12, and D is 16.
So, option A, 4.
Option C or D?
So, A now, coordination number for FCC will be the 4.
Okay, so you're saying the coordination number for the FCC is 4. Okay, how many of you agree with her?
Yes.
Like, yeah. Anybody? Anybody there other than her? Anybody willing to answer? Okay. If Okay, unfortunately, option A is not there, or fortunately, option A is not there. Otherwise, our basic understanding of the physics will go wrong. So the coordination number is the number of the nearest atom, the first nearest atom. And if I draw the FCC structure, as I draw the FCC, you guys will come to know that okay, it's uh, anyway 12. So say if I'm drawing the FCC, so FCC is like you have atoms at the corner, right? And then you have at the center of the faces, each face. So here. So six faces are there. The six atoms should be there on the faces. Now, if you have to ask the coordination number, then these four are say these. Okay, let me just choose some other color. These four are there. One, two, three, four. They are the nearest. Then this atom is also equally distant. This one, and this one. So 4 and 4, 8. Similarly, here these atoms will also be there, right? Of the next unit cell. So all of them are equally distant. This one, 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 this. All are equally distant. And the distance, if it is a, all of them are at a distance of a by root 2, right? And therefore the coordination number is 12. The coordination number 4 is there if it is like simple cubic structure. If you don't have any atoms which is there lying on the, like if it is a simple cubic where you have only atoms at the corner, no face centered, then in that case, yeah, 4 atoms will be there. For example, if you see this one, so 1, 2, 3, like 4 and 5, total 6 will be there in that case. Yeah, 1 on this side. Then in that case, the 6 will be there for a simple cubic. Yeah. Before I take the next question, I just want to know how many of you are like uh, from. Can you please introduce yourself, because I have like some uh, few of the opportunities are there in our institute, and accordingly I can maybe suggest you guys if you are interested in doing some. Okay, first let me ask, like, how many of you are interested in doing any research project into the in the ISC Bangalore or the similar institutes? Is there anyone who is interested to like work in the experimental lab to get an exposure how the things work, and those who are currently in their masters or about to start their masters or like in the final years of their bachelors? Are there anyone in the group? Because currently in our institute we have like some good openings for the interns for the summer project. Is there anybody? I don't think I don't see any response. Okay. But if you are really want to do the science and if you are pursuing a bachelor's or a BTech in this category, I would highly encourage you at least to get some exposure in the top tier institutes of India to at least know what's there in the science and whether it will be good to pursue for your interest. Yeah. And if this is the case, then I will just take the final question of today's, and then after that we'll end the class. So The question is, uh, let me give you some Lennard Jones potential on which the AFM machines work, and then calculate the effective separation distance between the atoms. So question is, you have the potential of a diatomic molecule as a function of the separation distance between them is given by Vr equals to minus A by R6 plus B by R12. Then the value of the potential at equilibrium separation between atoms is, okay. So this is the Lennard Jones potential. In this one of the term minus A by R6 is the attractive potential, and B by R12 is what we call the repulsive potential. And this governs why there are diatomic molecules, and along with that, it also tells why when the carriers are there, why don't they just merge into each other? Why the two atoms don't merge into each other? Because one of the term is repulsive. When you go very close to the value, basically, when the atoms come too close, the electronic cloud repulse each other. That's why the repulsion term is there in this potential. And if they go too far, then basically electronic clouds make the opposite polarity kind of thing, and then it attracts each other. So and those are the van der Waals attraction. And in that sense, basically, this Lennard Jones potential form is there. One term is attractive, another is repulsive, and at the minimum of the potential, your your diatomic molecule is stable. And if your any system is stable, in that case, your force should be zero, right? If the force is there, then how would your system be stable? So for that, your force has to be zero, and we know that F is proportional to del V by del R. So we take the derivative of the given Lennard-Jones potential and take it to be zero, right? So let's just differentiate. So if we differentiate del V by del R, what we will get is 6A by R to the power 7 minus 12B by R to the power 13. Setting it to zero, setting del V by del R equals to 0 gives 6A by R to the power 7 is equals to 12B by R to the power 13. Now you can solve it for the R, value of the R, and what you will get is R to the power 6 is equals to 2B by A. So this is the value of the position basically. This is the position at which your potential will be stable. So if I draw the potential form, it will be, okay, let me just, yeah. This is, I'm drawing the potential VR as a function of R. The potential has the form like this, and this is the point where it's del V by del R is 0, and this is 2B by A. This is what it means. And at this point, your in this region it's repulsive, your potential, because it's positive. Here it's attractive, and here it's minima. When your potential is minimum, then your electrons are basically trapped in that one. Your atoms are trapped in that one, and that's where you'll get this most stable state. Now, since you are known, okay, the question asks what is the V minima basically. V R minimum in this case. That's what we have to calculate. So let's just substitute the value of R6 into the given form of the potential. So the given form of the potential is minus A by R6 plus B by R12. Substituting, this is equation 1. 2. Substituting equation 1 into, what we get is minus A by 2B by A plus B by 4B square times A square. If you just solve it, you will get minus A square by 2B plus A square by 4B, which will give you minus A square by 4B. So this is the value of the potential at this point, a minimum potential. So V minimum is nothing but minus A square by 4B. This is the answer to the question, and this is known as the famous Lennard-Jones potential. This form is known as the Lennard-Jones potential, where A is the this attractive part and B is the repulsive part, which makes the potential go blow up at the low values of the R. So yeah, so I think this is for the today's class. If you have any question, you can ask. I'll be happy to address your concerns. Yes, question time. By the way, what you guys are doing, like, are you like a bachelor student or have completed your masters or currently in any state university? Or what are the positions which you are holding right now? Like, I know you are students, but like, at what stage of you are, like, in your, at least in the educational background?
Myself, Komal, I'm doing MSc second semester from Banaras Hill University.
Okay, you are from BHU. I see, I see, I see.
Yes, sir.
Yeah, I think in the BHU, a new faculty is there, Saurabh Srivastav. I don't know whether you know him or not. He's a good friend of mine. I think he recently joined there as a faculty. So he's a brilliant researcher, as far as I know. Some good research on the graphene-based system only. His PhD.
Hello, sir. Myself Dipanita.
Yeah,
Now I am pursuing PhD in ICT Bhubaneswar. My guide is Dr. Ramakant Naik.
I
Now
see, I see.
my coursework is going on.
Okay, okay. So, and you can like use your NPTEL certificates to complete your
Y-
coursework, right?
Yes, sir. Yes, sir.
I see, I see. Nice, nice. And like looks like you are like from you guys are from the good educational background. That's what I was asking. Like if you any of you wants to do an internship, like those who are already enrolled in the PhD, they are there. They have to complete their research work there only. But those who are like not in yet the position basically and have just completed their bachelors at ISC Bangalore, we have some good opening for the interns. And they can come here, can do the fabrication part of the this lithography, all those things, to see how we make the micron scale or nanoscale devices. And those are the ones which are like basically the cutting edge research which is going on in India and the worldwide, and they might get the exposure for that also. If there are no more
Yes,
questions.
sir. I have a question, sir. Is every Saturday there will be held this interaction session or only this time?
Okay, so every Saturday from 6 to 8, this will be there. uh, yeah, so every Saturday it will be there till the coursework is there till the point.
Okay, sir. Thank you, sir.
Yeah, if there is any change in the schedule, you guys will get it notified from by email. Yeah. So if there are no more questions, then let's just conclude the class. Okay, it was a good time with you guys. I'll just stop sharing my screen.